In today's video, I wanted to take some time to talk about a really popular problem for applying different methods of optimization to, in which we solve finding the distance between a point and a plane in three different ways. So I have our example here that we're going to work through, and I'm going to talk briefly about the first method, but then really focus mostly on the last two methods. So let's go ahead and get started. All right, so in this example, we're going to try to find the distance from the point 1, 2, 3 to the plane that's given by 2x minus 1 minus 3 times y plus 2 plus 4 times z minus 5 equal to 0. And the three different ways that we are going to do this is, well, the first thing we're going to do is try to do it without calculus, which I really probably won't show in any detail, but I'll briefly discuss it. But then the two big ones are actually going to be making a reasonable substitution and then minimizing an appropriate function of two variables, and then using Lagrange multipliers as our last method. Okay, so really, honestly, this first method I don't really want to spend too terribly much time with, because I actually go into detail on how to do this in a different video. So I'm actually going to recommend that you check that out. When we say without calculus, we just mean not using like the derivative or the integral or anything like that. You can really just use that scalar projection that we talked about in my video of where I compare and contrast scalar and vector projection. So check out that last example there to figure out how to do part A of this problem. So we do this with the scalar projection, as shown in my other video. Okay. So like I said, I really want to focus on B and C, since those are more closely related to the concepts that we've been talking about lately. So part B, let's go ahead and jump into that. Making a reasonable substitution and then minimizing an appropriate function of two variables. So what will that look like? So we have B. I think that before you can start really making a substitution, it probably makes more sense to talk about what this appropriate function is and figure out what exactly it is that we're going to have to substitute into. So let's start there. So our appropriate function, this is what we're trying to minimize. And if we go back to the statement of the problem, we want to find the distance from a point to the plane. So what we're really going to wind up minimizing here is going to be the distance, okay? So we're minimizing the distance between the point and something that is on that plane, specifically a point. So perhaps an appropriate function, at least to start with, might be the distance between 2 points. So and that function is given by d of x, y, z is equal to the square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared, where the x naught, y naught, and z naught are our given point that we really want to know about the distance with respect to. So the goal is going to be ultimately to minimize this guy with our point plugged into it. But before we do that, honestly, in any context that we're going to be minimizing, you can think about, or minimizing using calculus, we're going to be looking for the gradient. And quite frankly, when we start looking at derivatives using this square root function here, it gets quite messy quite quickly. And we notice that minimizing the square root function is really actually going to be the same as minimizing just what's on the inside. So I'm going to turn this into an alternate function that we can use to minimize this. We'll call it f, I guess. And I'm just going to square this, okay? So f is going to be equal to d squared. So we're going to have f is equal to x minus x naught squared plus y minus y naught squared plus z minus z naught squared. And this is actually what we're going to minimize, because finding the minimum here will give us the point that we need to minimize this as well. And I guess I should probably go ahead and plug in the point that we're working with. So it's going to be minus 1, y minus 2, and then z minus 3 squared. Okay, great. So now we have our so-called appropriate function. So this is what we're trying to minimize, but we have this kind of restriction, right? Our goal is to minimize the distance function in such a way that it lands us at a point that is on our plane, okay? And so we have to figure out how to incorporate this information into this function. And the way that we're going to do that is by rearranging for z and then plugging that in to here. And then we get a function just of x and y. So our goal is to find a point on the given plane. So what we're going to do is solve for z and substitute. So solve for z in plane equation. And what you're going to get when you solve for z is going to be the equation z is equal to 7 minus 1/2 x plus 3/4 y. And now we can take this right here and plug it into z here. So the function that we are going to be minimizing, which I'm just going to go ahead and write it as a function of x and y because that's all that's going to be in it. So I have x minus 1 squared plus y minus 2 squared plus, and then this whole thing right here. And then minus 3 squared. I guess I can simplify that a little bit. Squared. Okay, great. So this is actually what we're going to wind up minimizing. And the way that we're going to do this, since we really just have boiled this all down to just this one function, we took our constraint and we absorbed it into the function here. So since we've kind of already included that, all we have to do is work with where the gradient is equal to 0, like so. Okay, so that's what we're going to want to wind up solving here. Our gradient is going to be equal to 2 times, we're going to get x minus 1 plus 2 times 4 minus 1/2 x plus 3/4 y, and then times negative 1/2. And then I guess I'll put my second component on the next line here, because otherwise I will I've run out of space. We have 2 times y minus 2 plus 2 times 4 minus 1/2 x plus 3/4 y times 3/4. Okay. A really common question that I've gotten so far has been when taking this gradient right here, do we want to FOIL out this expression, or not that expression, this expression down here, and then simplify and take the gradients? The answer to that is you can, but you probably don't want to. It is much easier to do what I just did right here and apply the chain rule instead. You get a much cleaner answer and much less likely to make mistakes then. Okay, anyway, remember that we want this to be equal to 0, 0. So we're going to wind up with a little system of equations, not like we do in Lagrange multipliers. This is just going to have two systems, or two equations, two unknowns. It's that 2x minus 1, and then I guess here we get minus 4 minus 1/2 x plus 3/4 y. That's all equal to 0. And then we have the 2 times y minus 2 plus, and then if we simplify this, it's 3/2 y minus 1/2 x plus 3/4 y equal to 0. Now, this system of equations is much easier to solve than what you might see in Lagrange multipliers, because at this point, I guess it looks a little bit messy, but it's really just, I mean, you have the x and the y's, none of them are squared or cubed or anything like that. Combine all your like terms, and it's really actually quite straightforward to solve using the standard methods that you would have learned in high school or like algebra 2 or something like that. So applying those ideas, what we get then is x is equal to 69/29 and y is equal to -2/29. Okay. Now, at this point, we have two parts of a component that we could plug back into our distance function here. So in order to be able to do that, what you would do is take the x and the y, plug them in here, get z, and then you would have all 3 points to put into the distance formula. However, mathematicians can be a little bit on the lazy side, and what we are going to do is notice that, well, remember that the big goal here is distance, okay? Remember that the goal was distance. And what we can do then is note that our function, capital Fx, is equal to the distance function squared. And notice that this guy does not require z to be able to solve for it, okay? So we can really get the entire distance that we're looking for, because we don't actually care about the point itself, we just care about the distance, by taking the square root of the x and y that we found plugged into the function f. And that function f was, again, this guy right here, okay? So you take those two values for x and y, plug them in there, simplify it down, and what you get when you take f of 69 over 29 and then negative 2 over 29, square root of 400 over 29, which is just equal to 20 over root 29. So that is the shortest distance from the point that we were given to the plane. And if we had actually done part A, gone through and went through all those computations the same way that we do in the other video that I posted a while back, you're actually going to get the exact same answer, okay? So like, you go through all this work and you want to check to make sure you got the right thing. Well, you can try the without calculus version, which is a little bit faster, honestly. But the point is that you can still apply this method and get the exact same answer, because a lot of different things can really be just kind of boiled down to some form of an optimization problem. So, okay, let's kind of recap a little bit what happened here, because there was quite a bit. All right, so our goal was to try to find the minimum distance between the point and the plane. So we started with our distance function that is going from the point that we were given to some point that will hopefully wind up being on the plane, which we guarantee by saying that z has to have this particular relationship with x and y, and then making that substitution. So, and we're going to see here in a little bit when we work with Lagrange multipliers, there are two ways to deal with a constraint that you've been given. When we look at this problem, we can kind of think about this as, okay, we have a function we're trying to minimize, and then we have our plane that is our constraint. And our options are to either A, or, I guess C, use Lagrange multipliers, which is kind of pops out pretty much immediately in the setup. Or what we can do is try to incorporate our constraint into our function, which is really more or less what we've done by going through this process here and substituting in a rearranged version of our plane into the function that we are trying to optimize. So just a couple of different ways to approach that. But anyway, you go through all that work and you wind up with the distance at the end, 20 over root 29. Let's do the Lagrange multiplier method now. So in this case, again, our goal is to minimize. I'm going to go ahead and use our modified version of the distance function where we've squared it. Now, I do want to stress that we are not substituting for z here, okay? Notice that this is still in terms of z. It's got all three variables in it, because when we do Lagrange multipliers, we deal with our constraint as an actual second part, right? So we have, it's subject to the constraint, g of x, y, z is equal to 2 times x minus 1 minus 3 times y plus 2 plus 4 times z minus 5, and that's going to be equal to 0, okay? So this is what we're minimizing, constrained to our final point, x, y, and z, winding up on this plane, okay? So Lagrange multipliers tells us that the gradient of f has to be equal to lambda times the gradient of g. So gradient of f, that's going to be 2 times x minus 1, 2 times y minus 2, and 2 times z minus 3. And our gradient of g is just equal to 2, 3, or 2, -3, and 4. So, and that will give us this system of equations here, where we have 2 times x minus 1 equal to 2 lambda, and 2y minus 2 equals to -3 lambda, and then 2 times z minus 3 is equal to 4 lambda. And then finally, our last equation comes from the constraints. 2x minus 1 minus 3 times y plus 2 plus 4 times z minus 5 is equal to 0. Okay, so now we just have to solve this system of equations, which Lagrange multipliers, the setup for the most part, typically pretty easy. Solving the system of equations, maybe not so much. We're going to be able to do this by using the strategy that we would have used in, I don't know, actually we've used it a few times now. The main goal here is going to be to get one side or the other of these equations to all be the same. And I'm actually going to, I noticed that there's a lambda all along here and there are 2's all along here. So I'm going to do what I can to try to make lambda over 2 over here and then make the appropriate changes over here to make that happen. So specifically what I'm going to wind up with then is, well, 1/2 of x minus 1 has to be equal to lambda over 2. And then here I have -1/3 y minus 2 is equal to lambda over 2. And then my last one here is 1/4 z minus 3 is equal to lambda over 2. So basically what I've done here is gone through and swapped out these coefficients that are here. Okay, so now that all three of these are equal to the same value, lambda over 2, lambda over 2, lambda over 2, we can set these all equal to each other. And one thing that I really want to point out that I didn't mention is that there's really no good way to make sure that x, y, z, and lambda aren't equal to 0. So we have to kind of be careful to not accidentally divide by any of those values somewhere along the line. And so far we've done pretty well, okay? So now I'm going to get that x minus 1 over 2 is equal to -y plus 2 over 3, which is equal to z minus 3 over 4. And again, that just comes from setting all three of these equations equal to each other. And now I need to start kind of solving some things. So the first thing, I'm just going to go ahead. We can start with these two guys right here. And simplify some things down and see what happens. So if I have -y plus 2 over 3 equal to z minus 3 over 4, rearranging this, putting the x and or the y and z on one side and all the numbers on the other side, what you wind up with in this case is it's going to be 4y plus 3z is equal to 17. And that's as much information as we can get out of those two. So honestly, our best bet to be able to either continue solving is to hope that something nice shakes out from working with maybe a couple of others, or, you know, ideally, we're going to find another equation in terms of y and z to do the whole 2 equations, 2 unknown, apply the algebra 2 techniques, and then be able to solve for y and z that way. So let's kind of start thinking about that a little bit. We can look at these 2 equations right here, the x minus 1 over 2 equal to z minus 3 over 4. And in simplifying this down, what we're going to get, we have, I'm going to multiply both sides by 4 here because that'll get rid of my fraction. I get 2x minus 1 is equal to z minus 3. Well, that's pretty convenient because if I look back over here at my constraints, I notice that I have a 2x minus 1 here. So this is kind of a strategy that maybe I haven't mentioned quite so far, just in the sense that keep your eyes open for maybe somewhere along the line something pops out that already exists somewhere else. And then you can make a substitution that way without having to simplify everything down and then re-expand everything back out and so on and so forth, which eventually would work out. You absolutely could do that, but this is really convenient. I'm just going to swap that out for a z minus 3. So my 2x minus 1 plus, oops, nope, that's a minus 3y plus 2 plus 4 times z minus 5 equal to 0 is now going to become z minus 3 minus 3 times y plus 2 plus 4 times z minus 5 equal to 0. Okay, once again, we can simplify all this down, keep all the y's and the z's on one side, move the constants over to the other, and what we're going to get out of that is that negative 3y plus 5z has to be equal to 29. Well, I said when I was looking at this that if I had another equation that had only y and z in it, I could use that to solve for y and z. So I'm going to put these two pieces of information here together. And I'm going to solve for y and z. And when I solve for y and z here, what I'm going to get, again, using just the standard algebra 2 techniques, you can use substitution, elimination, whatever suits you. What you're going to get is that z is equal to 167 over 29. And then plugging that in, you're going to get that y is equal to negative 2 over 29. And then if you take this value for z here, plug it in here, solve for x, we are eventually going to wind up with the fact that x is equal to 69 over 29. Now, these last two values look really familiar. They are exactly the same as the two values that we got using our other method. See here. Yeah, 69 over 29 for x and negative 2 over 29 for y. And that makes sense because all we've done is take the exact same problem. Okay, we started with the same objective function, we started with the same constraint, and we just approached it two different ways, but we should expect to get the exact same answer here. Okay, and if we had gone through and solved for z in that other version of the problem, we would have gotten the same number there as well. Okay, so this is our point, right? That's the actual point on the plane that is closest. However, we still have to figure out what the distance is. And remember that the distance, if we look back at what we started with, we were actually minimizing the distance squared. Normally there would be a square root sign on here. So our distance is going to be the square root of our objective function f evaluated at this point here, the 69 over 29, negative 2 over 29, and then the 167 over 29. And you plug that back into your function f, and you're going to get, once again, 20 over root 29, which matches what we got on the other one. So all of this is to say that you are able to solve optimization problems in multiple different ways. And also you can turn problems that maybe you didn't expect to be an optimization problem into an optimization problem. So I really want to emphasize that when you're working with like finding critical points with the gradient being equal to 0, you really need to try to make sure that you take that constraint and that you're plugging it into your function somewhere to make sure that you're accounting for it. But that's only with using the gradient being equal to 0 type method to find your critical points. Now, when you're working with the Lagrange multipliers, however, you do not want to make that substitution, right? The Lagrange multipliers, we have our constraint. It's dealt with separately in a way by taking it and saying, okay, it has to be equal to, or gradient of f has to be equal to lambda times gradient of g, just like that. So anyway, that's pretty much all there is to this problem. So part B is probably, I guess, maybe the most difficult in trying to figure out how to set that up, and then also just figuring out, okay, what function am I supposed to minimize? But a lot of that is just kind of like trying to figure out the context and stuff like that. So anyway, that's pretty much it. I'll see you guys next time.